All right, here we go. This is problem number 107 from chapter 4 of the Halliday and Resnick book. So we've got this particle here that's going around in a circle. I'm pointing, you can't see what I'm pointing at. It's going around in a circle like this. We're given our radius, 3.00 meters. And we know that the period is 20 seconds, right? Because it says it completes one revolution in 20 seconds. All right, and then we know that at time 0, our position is 0. Now, we got to do something a little bit weird here. So they've called this distance here, they've called this our radius, which is 3 meters. Now, the question wants to know some information about the position at certain times. So your position, remember, is actually the distance, the vector that points from the origin to the object's location. So it's this. And unfortunately, we usually use r for position, but that overlaps with our radius, and our radius and our position are not equal in this problem. So for this problem and this problem only, I'm going to use d to represent our position as sort of our distance from the origin, okay? So again, for this problem and this problem only, we're going to use this guy to represent position, and then we'll use r to represent radius so that there's no confusion between the two, okay? So that's the deal. So what we just learned then is that our position at time 0 is 0. We're at the origin, okay? So based on that, we can make some pretty simple observations. Specifically, we know that this is our position at time equals 0, and it's going to take 20 seconds to go around. So that means it's going to take 5 seconds to get here, right? It's going to take 7.5 seconds to get there, and 10 seconds to get there, right? Which is going to help us for question A. So question A wants to know what's the position after 5 seconds. I'm being a little bit sloppy with my notation there. Okay, well, our position after 5 seconds, well, you've moved horizontally 1 radius and vertically 1 radius. So my position there is going to be 5. Nope, I keep wanting to make the radius 5. The radius is 3. So our position there is going to be 3i plus 3j, and that's all in meters. Now the problem does ask for magnitude angle notation. I'm going to assume that you guys convert this, can convert this, right? Because that just means 3 meters this way, 3 meters this way. Here's our displacement vector and the angle, right? So I really wish they'd asked for it in unit vector notation, because I know you guys can do that. All right, so B, we want the position after 7.5 seconds, right? So now what we got to do is find the position here. So a little bit of extra work. So there's a little red triangle here, right? And it's got a hypotenuse of 3. So it's going to look like this, 3 meters. And then you've got this guy and this guy, right? So you can do a little bit of trig, and you'll find out that this side over here is 3 divided by the square root of 2, and this side is 3 divided by the square root of 2. So write that out as a decimal, right? And then, so your position at that instant is then going to be this guy, right? So your x-coordinate is going to be 3 divided by the square root of 2, and then your y-coordinate is going to be 3 plus 3 divided by the square root of 2. So you're going to get 3 over the square root of 2 is your x-coordinate. And then your y-coordinate is going to be 3 divided by the square root of 2, but then you got to tack on 3 because we're, sort of up a little bit here, right? So J, and this is all in meters, okay? So, and obviously you can use your calculator and convert this to decimal notation, which would be, sort of more acceptable in physics speak. All right, and then finally, question C wants to know what the position is after 10 seconds. Well, after 10 seconds, you're up here at the top of the circle, right? And so our position there is just going to be, well, we're 2 radii up, so 6 meters in the j direction, right? Okay, so that's A, B, and C. All right, let me erasify this, clear up some room on the board. All right, question D wants to know the displacement from 5 to 10 seconds, right? So okay, question D wants to know the displacement from 5 to 10 seconds. Well, look, you're just going back 1 radius and up 1 radius. You're going back 1 radius and up 1 radius. Okay, for that interval, find the average velocity. Well, so for part D, we just found our change in position, right? And we got negative 3.00 I plus 3.00 J, and that's all in meters, right? For E, we want the average velocity. Well, oops, that's not what I want to do. Average velocity is, by definition, change in position divided by time. So I'm just going to take my position, change in position that I just found, and divide it by the time that it took. Well, that's 5 seconds, right? So you just divide component-wise, and you'll get negative 0.6 I plus 0.6 J meters per second. Okay, so that's D and E. Let's see, F. So F and G both ask you for the velocity. Well, I probably should have done this right from the start. You can find your velocity because we know the radius and the period. Well, technically you can find your speed, right? 2 pi r, you can find the magnitude of the velocity. So plug your numbers in and you get 9.42 meters a second. Sorry, 0.942. 0.942 meters a second is the magnitude of our velocity. It's our speed. And at 5 seconds, let's see. At 5 seconds, we're going up, right? Oops, that's the worst upward arrow anyone has ever drawn. But remember, your velocity vector is tangent to the surface of the path that it's following. So that gives us 0.942 J. And then at 10 seconds, it's going horizontally in a negative x direction. So there's that. And then to find your acceleration for h and I, so h and I want the acceleration. Well, acceleration is v squared over r. So plug in your 0.942 meters a second. Don't forget to square it. Divide it by your radius, and you get 0.296 meters a second squared, and then you just got to put in your direction, right? So check it out. After 5 seconds, remember the acceleration always points in. So after 5 seconds, it points in a negative x direction, and after 10 seconds, it points in a negative y direction. All right, so there we go.